Yeah, so just to recap, the first requirement that we discussed, our scene representation should have is like viewpoint invariance. The second one is grounding of semantic concepts. In this case, it's the milk, but it should be all other concepts that we use in natural language. And this is called the symbol grounding problem, the symbol being the word or the semantic concept that we have, and grounding meaning like in the physical world. The third thing is it's not only enough to ground symbols or concepts in the physical world, but we should the representation should also encode somehow traversability. That is, if you tell a robot to go fetch me a cup of coffee, it should know not only the grounding of where the coffee is and where it is, but also a shortest path or a path to go from where it is to the coffee. So the representation should have traversability and obstacle information. So that's the third requirement. The fourth requirement uh, uh, is what I would like to argue is that the scene representation should be hierarchical. Now, why is this the case? So if you notice carefully, humans perceive and organize things hierarchically. So my location or anyone's location, geographic location is a hierarchy. You're in a building, in an institute, in a city, in a town, etc. Also, the way we arrange objects in a room is also known to be hierarchical. So for example, this paper sort of did an analysis of how people organize objects in a room. It turns out that in a room, objects are organized more closer to some anchor objects. So for example, in the kitchen, you'll find bowl and a plate more closer to a table, which could be considered like an anchor object. Similarly, in a bedroom, a bed would be an anchor object. So there's some hierarchy, and this is nothing new. This realization, people have used this to develop generative models for scenes. So for example, that's a 2014 paper in graphics that uses such hierarchical structure to devise probabilistic grammars for generating indoor scenes, and it has been used for procedural generation of like indoor scenes. So, so the fourth requirement is like hierarchical. The fifth and the final requirement that I'll say is a low memory requirement. Now, so why should we have a low memory requirement? Ideally, we want our robots to go around in a large, to travel in a city, a large city, or maybe even crisscross a large country without having you to manually fix it. So it should, you need like low memory requirement for long-term autonomy. So that's the fifth requirement. So the five postulates, just to recap, of a good scene representation is invariant to viewpoint, grounding of semantic concepts. It should encode traversable paths and obstacles. Fourth, it should be hierarchical. And fifth, it should have low memory requirement for long horizon autonomy. Okay, now the way we at Spark Lab have been thinking about is like developing these 3D scene graphs. Armani and others and sort of first proposed this idea and gave like a semi-automatic pipeline to constructing 3D scene graphs, and a bunch of people in my lab built proposed 3D scene graphs using like a fully automated system. And the way the scene graphs are is like the lowest layer has like a metric semantic mesh, which is constructed from a 3D reconstruction pipeline. Then you extract objects and agents from that. That's layer 2. The third layer is places, which basically are free space points in the 3D space where robots can move. And these places layer basically will give you the traversability if you want to go from one point to the other. The fourth layer is the rooms layer, which is like a collection, which is like a collection of places, and buildings is like a collection of rooms. So, and you can keep building hierarchies on top of that. So this 3D scene graphs is hierarchical, so it meets that requirement. It is not, it has the viewpoint invariance because it's constructed from 3D reconstruction. Then it has the places layer, so it has the traversability information, and it has some grounding of semantic concepts in terms like objects, rooms, and buildings. So it meets all our 5 postulates. So what I'm going to show in a few slides is a very simple thing which shows that the hierarchical representation also gives you memory efficiency. And the way to think about this is like consider like a flat or a voxel grid representation where you have V by delta cube voxels, V being the total volume and delta being your granularity that you want to choose. And let's say you have also done the symbol grounding problem in this representation. That is, each voxel now has a label. So then the memory requirement would be like order L times your number of voxels. And this is not quite scalable. But the moment you organize things as a hierarchy, what happens is that the multiplicative term L times V by delta cube becomes like an additive term. So now you just have to store uh, the number of semantic concepts that you have in terms of rooms, buildings, objects, uh, but you still have that one V by delta cube term, which is all the voxels. So that simplifies to an extent, but then you can still sparsify and make it more memory efficient, doing a more lossy compression. And the way you do that is like you remove the voxels and only keep the places nodes, which are like this free space. And the reason you do this is because let's say you have visited the this building and you go somewhere else, and now you want to come back. You have most of the information that you need. You know the traversability, you know the grounding of concepts, like you know where the objects in the room and the locations are, and you probably don't need the voxel, which is like a very high memory intensive thing. So that's on the representation part. So given now that we know how our 3D representations look, we would like to construct them in real time. And in Hydra, so we propose like an incremental construction of such scene graphs. So this is constructed from just images. So basically you have a 3D reconstruction pipeline that computes Euclidean sign distance field, and we assume that that is given. From that Euclidean sign distance field, we extract a mesh. From the mesh, we extract places layer um, by solving the generalized Voronoi diagram, and from the places, by aggregating the places, we are able to get rooms. Now, I won't go into the details because I want to focus more on the structure part of this. But to tell you the story short, we are able to construct this in real time. And one of the important things in this is that because the scene graph is hierarchical, we are able to do better loop closure detection, because now you not only have loop closure detection based on visual features, but also you know which objects are near to your location and your previous location. You can use that information to detect better loop closure. So you see that at the last minute, it will sort of snap and become 1. There you go. So yeah. So this is a real test on a Unitary A1. We have a sensor payload with the RGBD camera, and it's going around. So this is next to our lab. So we'll build a 3D scene graph in real time. So I'll probably just let it play. What I want to mention here is the only place that it is using neural network is in is a segmentation, is a pre-trained segmentation network. So there's no other neural network right now. So it goes around, builds a 3D mesh. It identifies a bunch of places nodes which are free space, and then collects those places nodes. You can see the red color one places are collected as a room node R0, and the yellow colored places are connected as a room R1, and all of them is connected as a building. Okay, so this is cool. The thing is, like, Hydra works on diverse scene. So this is a simulated data set, like on split apartment. It works on like multi-room offices. This is again simulated, but a subway station. And the final one is MIT dorm. So this is a real data set that we constructed, and the size of this is like pretty large, 500 to 700 meters from one end to the other, and we're able to do like pretty good scene graph reconstruction. Yeah, so this is something that I said. So, but we're able to test and so get 3D reconstruction on simulated environments as well as on real data. So that settles the second part. So we looked at what the scene representation should be, and we have an algorithm to or a pipeline to construct in real time these 3D scene graphs. So the third thing that I want to talk about, and which I'm most excited about, is the structure that these 3D scene graphs have. So it turns out that they are hierarchical, so that is one plus, but there's a peculiar hidden structure that you can use, that they exhibit, and you can use to develop much efficient algorithms. So what is this representation? This scene graph representation is essentially a graph, right? It's hierarchical graph, but it's a graph. And graphs are good in one sense, but they can also lead to like NP-hard solutions. So if you want to solve any graph problems, they can be quite tedious. But it turns out that there are some graph parameters which, if you bound, then most of the graph algorithms become like polynomial time in complexity. And one such parameter is the tree width of a graph. And tree width of a graph is basically, the way to explain it is like, so if your graph was a tree, a lot of algorithms are very easy to, you get polynomial time complexity. You want to find shortest path, or even do graph isomorphism or inference on graphs, it's like polynomial time in complex. But for general graphs, that is not. So a graph decomposition is a way to sort of push the graph to be like a tree. So here on the second graph here, so we sort of mold it so that it becomes a tree. And in the process of molding it, what we do is we make nodes that are close to one another. Uh, we merge them and sort of pretend that is just one node. And the tree width is defined as the size of this which is k minus 1 for some technical reasons. And it turns out that many graph algorithms have complexity which is polynomial in n, but exponential in graph tree width. So if you have a bound on graph tree width, all your algorithms on graphs become polynomial time complexity. So which will give you like efficient solutions. Now, just an intuition as to why this is the case, think of a graph which is like connected, every node is connected to everything else. Now, if you want to optimize something by, say, changing one variable or one node, then you'll have to manage how all the other nodes have to change so as to affect this function. But let's say a graph has this sort of structure, right? Then if I change one of these variables, then I only have to manage those nodes that are in that clique. So therefore, you have only exponential of k minus 1 number of variables to look for. So that's sort of the intuition. But this is sort of true for a lot of problems, including like exact inference on graph isomorphism, and many other problems. In fact, there's like a well-known result on complexity of inference on graphs that low tree width is the only structural parameter that can ensure tractability. So that is the bounding, only that parameter can give you polynomial time inference. Okay, so this is great. So why am I telling you this? It turns out that tree width of indoor 3D scene graphs does not scale with the size of the graph. So you can bound a tree width of 3D scene graphs irrespective of the size of the environment that they explore. And the way we prove it in the paper is twofold. One is that the scene graphs are hierarchical. So we can show that the 3D composition of a hierarchical graph you can form by concatenating 3D compositions of each of its layers. And the second one is a more empirical result, which we show that the tree width of each of its layers is also bounded. And in fact, we sort of argue and prove it for the room graph as well. So it turns out that the room graph mostly have like tree width of 2 and no more. So that's great. So what it means now is the 3D scene graphs, you can do polynomial time graph algorithms with for all kinds of graph problems. And so we use this in one specific application, which is like in graph learning. So when you have a 3D reconstruction like this, right, you have some missing node labels, especially you don't know the rooms and building nodes, and probably we want to learn them. So we propose a neural tree solution, which what it basically does is, given a graph, it sort of constructs a new graph, which is H tree, which is formed by adding those 3D compositions. And we run message passing on the 3D composition instead of doing message passing on the original graph. So you don't do graph neural network on the original graph, but you do it on this new structure H tree, which is sort of coming from the 3D composition. And that has basis in the probabilistic inference literature. And once we do that, yeah, what we observe on the table in the right there is like you get quite significant gains. So if you do message passing on the input graph versus on the neural tree, you get quite a sizable gain. We also have like a theory result explaining why and sort of the number of parameters that it will need, which is like, again, this is basically proving the old thing that I showed, which is the complexity is exponential in tree width and polynomial in n in another flavor. And so I want to explain like the intuition why this happens, because there's an increasing thing that is going on, which is like using graph neural networks on scene graphs to do inference. And this is the why you should think about not using graph neural networks directly. So there's a whole literature on probabilistic graphical models, and there are two algorithms people use. One is loopy belief propagation, and graph neural networks can be thought of as like a neuralized version of loopy belief propagation. But what is known as loopy belief propagation is approximate inference, whereas the exact inference is junction tree algorithm. And graph neural networks are known to have limited expressivity because they are, in my view, because they are neural versions of loopy belief propagation. And what we do is like a neural version of a junction tree algorithm, and that gives you the high expressivity that we saw in the table before. Now, so the point that I want to make here is that is sort of give you a caution as to why you should not directly apply graph neural networks, is because graph neural networks were developed by researchers focusing on social networks, and large social networks are known to have like high tree width. And what happens is that the bounded tree width solutions are sort of almost overlooked and not taken into account. But scene graphs and that we have low tree width, so we should exploit that, and so we can have like better solution, more expressive solutions on polynomial efficient algorithms. Okay, so this is just this is Hydra, which is the real-time construction of 3D scene graphs implemented with neural tree. So the pipeline is the same, except at the end we have added the neural tree to run real-time, and so it's now able to label rooms as well. So you can see it has labeled something as kitchen, something as dining room, but it keeps changing because it sees new things and it sort of tries to recalibrate what it has inferred. Yeah. So yeah. So this was my talk. I want to like conclude. So the first thing we argued was like a scene representation. What should the postulates be of the for scene representation? We argued that in our view, we've been working on like 3D scene graphs as the correct representation of the scene, and we have a pipeline now of real-time construction. This opens up many opportunities. So rather than using images or some implicit learned thing, you can use 3D scene graphs to do downstream tasks. There are still open challenges to improving the 3D real-time construction. So things like representation of objects is still weak, and we're working on it. And the final thing, which is what I stressed on in my talk, which is this 3D scene graphs are a very special structure, and exploiting that is critical for developing better algorithms and learning models for downstream tasks. So I'll end here, and these are the references. Most of my talk will be based on like the most recent paper that we have under submission. And yeah, thank you, and those are all the co-authors of this work.
All right, thank you very much, Rajat. Are there any questions from the audience? So many. We'll start from the front.
Thank you for a nice presentation. And I'm wondering, how could we extend the scene graph to outdoor environment? Because in Hydra, it highly assumed that there are narrow space. So when we just perform erosion, and then we can divide rooms. But in case of outdoor scenarios, there are not the narrow scene. I mean, the narrow scenes are not guaranteed. So how could we adapt your concept to outdoor environments?
Right. So two answers to this. So the Hydra, if you run the pipeline, it'll run. The problem in the outdoor scene is the hierarchy, because inside you have a natural hierarchy which we sort of encode, right? So objects, then rooms, then floors and buildings. But outdoors you don't have that natural hierarchy. So extending it to outdoors, and that is the problem. And in fact, Gerard, who's a co-author, is working on outdoor scene graphs, and I think he has a talk and the oral presentation in this workshop as well. So about that. So he's using some nice ideas on outdoor. Yeah. So
Okay,
the other thing is like your point density. Yeah, that's a problem. So there's a trade-off between how dense you can reconstruct and real-time operation.
Other questions? We'll go over here.
Thank you for the great talk. I just had a quick question about the instance segmentations. You mentioned that a pre-trained network is used, which makes sense. I was just curious if how instance segmentation errors might affect the scene graph, or if there are any ways that the construction is accounting for potential over or under segmentation errors.
Yeah, so that does cause a problem. So what happens is you often have these issues of same object being represented as two objects, or two big objects is represented as one. So if you see a chair and there's something blocking, maybe it'll get represented as two. So those issues do occur. The way we do object reconstruction is by just geometric, by knowing that these things have to be closer. So there's one criteria, but that's an open thing. So we are working on like using maybe object models to sort of overcome that problem, so that we don't have to do reconstruction. But yeah, that is a problem.
That sounds great. Thank you.
Yes, I believe there's a question online.
So there's a question online from Jianhao Zhao, which is, could you please talk about future opportunities of using scene graphs for downstream navigation tasks and combining with language models?
Yeah, I think that's a great question. I think there's a paper by some other people in Spark Lab on that. And so it's open, like there's nobody has worked on it, and at least on not these graphs, but so the way people are doing language-based navigation is using like neural networks, and maybe this will give you a scope to maybe think about, or maybe not use them, or use them in a very limited way, and maybe more efficient way, because traversability paths are given. You know which object is where, so maybe you don't need that much of neural networks to translate a natural language query or a direction to a scene graph path. And that sort of provides a nice way. It can give you like more generalizability, because we're exploiting the structure that is there in the problem.
All right, I think we have time for one more question from the audience. We'll go over here.
Thanks for the talk. I was just wondering that the scene graph, the words are pretty like overused in various domains, and especially for like, for example, like VR domain, they were trying to using scene graph to I don't know, to interact or something. But so I was wondering, like, is there a key differences the word scene graph you're using in terms of like robotics or?
Yeah, we called it 3D scene graph. So I was not behind naming the thing. Luca was, so you can blame him. But I agree. So the first thing I think that I saw was like in Visual Genome, where they have 2D scene graphs, and yeah, I think it's going to grow, because it seems like a natural way to represent, and I think many people are going to propose their own way of representing it. I think that's all good. I don't see like a unified scene graph coming out so soon. I don't think there's a convergence.
Oh, thank you. And one more thing. And about the semantics you mentioned, I think it's pretty straightforward and simple. Like chair is a chair, but when it comes to like robot interaction, the robot has to know whether you can, like, for example, it's a chair, then you can see it, or you can move, or so a lot of semantics can be also added in your scene graph. Yeah. Are you planning to add more information about it?
Yeah, those are all open problems for this representation. So that, yeah, that's like, you can do probably PhD thesis on that. So I think.
Thank you so much.
All right, please join me in thanking Rajat for his talk.